Right. We actually got quite a bit further than I thought yesterday. So I really don't think we're going to use all of the 4 hours today. I'm guessing we're going to use around 2 hours, which will be really nice for you after that really long and hard day you had yesterday. So then you can have a bit more of time off between this session and the hydraulic session with Runa later today. So I think that will be a nice treat after yesterday. So we left off with radii and diameters. So we're going to continue on with chamfers and countersinks. Just gotta find my place here in my notes. So there it is. I think I'm going to kill the lights up front here, so it's a bit easier to see the screen. So the chamfers and countersinks. I'm not quite sure if you've really heard these expressions before, a chamfer and a countersink. Really, it just means that you have made an angle on what would otherwise be a 90-degree angle. You have cut it so that it's at a different angle. This means that, especially for smaller chamfers like this one, 0.6 millimeters times 45 degrees, what you are gaining by doing that is basically that you won't cut your fingers when you are handling it. Because a 90-degree angle on steel, it's going to be really sharp when you have machined it. So often when machining, you will put in these small angles, or maybe you will just put a note in the corner of your drawing or something that break all sharp edges with a chamfer of maybe 0.2 times 45. That was what we used in Imenco, which was really nice, because if there was a 90-degree edge and we hadn't put in a specific chamfer for that edge, then the guys that were manufacturing it would see the note. Oh, well, this one is going to have a 0.2 anyway. So they always did it. So and basically, when you have a 0.2, it is often more than enough to just have grinding paper or sandpaper type. So you just use that to create the edge. So it's often a manual task that is done. If it's a large one like this one, 2 millimeters times 45, then it's turned. If it's in a lathe, it's being turned, so it's done with tools and machinery. Or if it's in a mill, the mill will fix it. So, but for the really small ones, it is often enough to just grind it a little bit, just to get that sharpness away from the edge. And it's really nice for mechanics and everything that there aren't these really sharp edges that they will. Because not only will you cut your fingers, but you can cut straight through gloves even, and then into your skin. So it can be really sharp. It's more or less almost like a knife often. So it's very nice to just keep that in mind, that it's a good thing to avoid 90-degree edges. For the countersinks, those are specifically when you do it on a hole. When you have a hole and you create an angled edge all around the beginning of the hole. And it is often used because some bolts are shaped like this. And then you have the threads starting down there. So actually the entire head of the bolt has these 90-degree. It will be a 90-degree angle across there. So 45 degrees from the center line. And what you what you end up with then, if you have these countersunk holes, you can actually put the bolt in here, you screw it in, and then you have a flush surface. So the bolt head will be flush with the surface of the steel. So that if you have something that's supposed to be moving here, you can completely hide the bolt, and that way still get the use of a bolt, but not have it catch on anything that's moving. So that's a really nice feature to use. In Inventor, you can either create these edges in the sketch when you're drawing it in two-dimensional shapes, or you can wait until you have created your three-dimensional model, and then you can use functions on it and say, like, this edge here, it's going to have a 2 times 45 degrees chamfer, and then it will create this chamfer on it. So it's a pretty simple operation to do when you're using Inventor. Yeah. When it's flush, then it will be. So if we'll use the red here to show the steel, the material will come up here. So that the top of the bolt will become the same level as the top of the material. So usually when you have a bolt, you have these with a hexagonal head, or maybe with a round head or something. Then you will have the bolt head up here. Which means that in this case you will be able to slide something past here if there's supposed to be some movement here. Whilst in this case it will stop because it will hit the bolt head, and you will either block your movement, or if the movement, whatever it's moving, is strong enough, it will just tear the bolt head straight off. So that's a very nice feature with the countersunk stuff. And also, like, just for decorative purposes also, if you are putting on naming plates on your on whatever it is you've created some piece of equipment, and you want a plate with the name of the equipment and maybe some additional information. Maybe if it's something that's going to be used for lifting, you will have this workload limit, the VLL, stamped on this plate. And then it will just make a much nicer plate if you use countersunk screws on it, instead of using these that protrude out of the nameplate. So it just looks much nicer when you're creating it. Sometimes on squares, you will have squares and flats on cylinders, so you'll have a cylindrical, maybe a shaft or something, a cylinder, but you want, at the end of it, you're supposed to connect it to something that's square. Maybe it's something that's going to turn it so that it needs to have something to grip it on. So you will have these squares at the end in order to have something to grip onto the cylinder. So one way of showing it is like they've done here. They've shown it with a square symbol, and then the diameter, not the diameter, but the width of it. And then you have these diagonals, just to show that this is the point where it's supposed to be flat. It's not. This part is still circular, while this part is flat. So they have these diagonals showing that it's flat. You can also use this way of showing it, which is width across flat, basically, WAF. So it just shows that this entire flat area, which has these diagonals, it will be 17 millimeters across. So it's a nice way of just showing it. I haven't really ever designed anything using squares on it, but that's mainly because I haven't done much of rotating shafts or anything like that. But my personal experience is that usually you either use threads or you use some sort of splicing methods instead of these, but you might end up with them, so it's nice to just know that there is a way of drawing them. Sometimes you will have an arc, so that you will have sort of an angle in your part. Maybe there's a center here. So you will have an angle, in your material, and you will have an arc going across here. So the arc would have been circular if we continue it. So it will have a certain radius, which you can set here. Let's say R50, a radius of 50 millimeters in this case. But you can either give it the angle between the edges, or you can give it the length of the arc. So you either put it up like this. That would be an angle. But if you want it as the length, you put them as going straight up here, as shown in the drawing here, and you put this arc symbol in front. So they had 32 in this one, which means that the length from this point and across this entire arc to this point will be 32. So it's just a way of showing that if you put some flexible measuring tape and you put it here and you measure it all the way across here, you will have 32. So it's not the direct line across here that is 32. It is along the arc that is 32. And then we have threads, which is really important when we're mechanical engineers, because usually when you are making stuff stick together, you're either welding it or you are using threads so that you can bolt it together. So threads is something that is very important to try to get correctly in drawings, just to be sure that the bolt that you have designed to fit in there will actually fit. So that's sometimes a huge problem. I've seen a lot of different design errors done by colleagues and even myself, just because you've been in a hurry, you haven't really thought it through, and then this is good enough, and then there was something you didn't think about. So like if you just set that this hole was to be 20 millimeters down, instead of saying that this part which has the threads is 20 millimeters deep, and then the hole is supposed to be even deeper. Because what you can end up with is actually when they create threads in holes, they don't manage to get the threads all the way in. So that I'm going to try to draw this. So you have the bottom of the hole, and this is the point of the drill when you're drilling it in. So the drill has a certain angle when it's going in, so that's the bottom of the hole. So from this line on, it will have the same diameter all the way. So that's the pre-drilled hole before they start creating threads. And what they then do is, so long as it's a fairly small hole, if it's a large hole, they can put it, and this is a circular object, then they can put it in a lathe and they can turn it, and they can have a cutting tool going inside and just turn it all the way. Then you will be able to create threads almost all the way in. But usually what they have is that they have a tap die or a thread tap. It's a thread tap when it's in a hole. It's a die when it's external threads. So a thread tap, which is basically just it looks kind of like a drill, but it has threads on it. So it has these threads already on it, but it also has cutting grooves in order to allow it to basically cut material, and then you can transport the material outside. So it will come into it, and as you rotate, it will start cutting threads. But the point is, for this threading tool to get inside, it needs to have sort of a curve at the start. So here it will basically not be cutting much. And then as you get along in here, it will have proper cutting. So from around this area, you will have complete threads that are being cut. But the problem is that suddenly you have this length of tool that is not creating proper threads. The bolt won't be able to go past this point in the threads that are being made. So when you move this one into the hole, you're cutting your way down here, you will end up with a section at the bottom which hasn't got complete threads. They aren't deep enough for the bolt to actually enter them. So that's sometimes a huge problem, because then the guys at the workshop, they've just drilled a hole to 20, and then they've threaded it, but then you end up with the threads actually just going to here. And so your 20 millimeter long bolt that you were supposed to screw in here, it won't go all the way in. So it will stick out further than it was supposed to. So that's a very common mistake that happens. So, but there are, in this Metal Trades Handbook that you have gotten, the small blue one, there are actually a lot of references to standards and excerpts from standards which show, if you are creating this sort of threads, what is the length you should have. So if you're supposed to have 20 millimeters of length with threads, how deep does the hole have to be in order to create proper threads? So there's a lot of information in that book that will tell you how to do this properly. When it comes to external threads, they are usually, for circular objects, they are usually done in the lathe, so they are turned as they are created. But you often have taps that are sticking out of non-circular objects. So you might have a block with just a tip sticking out of it that's supposed to be threaded. And then you will use a tap die, which is sort of the reverse of this one, which is it's a square block which you put into a special tool that you can turn it around the entire tool. And then it is hollow on the inside, and it has these cutting grooves that will cut threads all the way down. So it's that's another way of doing them on the outside. But there you also have the problem that you can't get all the way in. You won't get them cut all the way in. So there you also have to take into account that if you intend to have a nut on top of here and you intend to screw it all the way in, completely flat, then you actually have to do something with the edges here. So you have to, if we create a section through it, so we have the same tip as we have there, only this one has been sectioned so that we can see a cut through it. So what it's possible to do is to actually create, because when they are turning this one, they will almost automatically get a slight radius there. It's almost impossible to avoid it. When you're doing it, you won't get a complete 90-degree angle in there unless you start changing a lot of tools and starting using completely fresh, sharp tools every time you're creating one of these. You won't get it. You won't get it into a 90-degree angle, basically. If you have a completely sharp cutting tool, completely fresh, you put it on and you start this, then you will get it almost like a radius of 0.2 or something, but there will still be something there. So one way of avoiding it is to actually create a slightly hollow section there. So when they are turning it, they actually cut into the material of the big cylinder. So they cut into it and create a groove around it, which means that the tools you are cutting down and placing on top here, you're turning it around, it's cutting, and as you get down here, it will actually become flat with this edge instead of stopping where this one was rounded earlier. But these are things that you will. What we should actually do was that we should have had a proper workshop where we could go and you could actually see how this works, but it's not that easy here. Like the school where I did my vocational studies to be a mechanic, we had half of the theory was done in a classroom and the other half of the theory was done in a huge workshop where we had all of the tools and machinery that we needed to show stuff. So it's a bit easier actually learning this stuff when you're on vocational studies than when you're in engineering studies. You just need to know the theory of it, and people think that you don't need to see how it actually works. But coming from the vocational stuff, I think it's highly enlightening to see it in real life. But we'll see. Maybe if I can try to find some examples that I can bring in one of the lectures so that you can get to see them. That would have been nice. So I'll try to see if I can find something. There are different ways of designating the threads in the drawings. So you can see here they have written M16 on both of these. So the M means that they are metric. So they are measured in millimeters, basically. So it has its own standard, metric threads. So it follows a specific ISO standard. And most of the world use metric threads. When you get to America, who are still using the imperial units, they tried to switch over to metric, but they switched back for some reason. So they are one of the few countries that are still using the imperial units. They've got the more or less the same threads as the metric ones. So you can actually, if you find the correct diameter metric thread, you can put it onto the inch threads, which the Americans use. So, but theirs are written as UNC. So it's for unified and coarse. With the metric ones, you can also have in the inch ones. You also have UNF, and that's just a designation on the threads on. If you see a cut through the threads here, the coarse and the fine ones, they're just a measure of how many threads do you have along 1 inch. So how many of these tips do you have along 1 inch? So for the coarse one, they have fairly few, and the fine ones, they have more and more. So there are many of the fine ones. The difference with them is that, of course, for the fine ones, which would have many of these tips, will take longer to screw it in because you have to rotate it more rotations in order to get it all the way in. But the difference in strength is actually that the fine ones, in order to have several tips, they have to have a bigger core diameter. Because if you have if you have more tips, you will have a shorter space between them, and since they are supposed to have the same angle all the time, of course the height of the threads will be smaller, which means that the diameter for the coarse threads will be smaller than the diameter for the fine threads. So actually, if you are designing something and you have coarse threaded bolts going through it, and you see that these are just not making it in the requirements that I have to fulfill, you can try to just switching them to fine threads, and then your design calculations might just work within the requirements. So it's a nice way of tweaking designs sometimes. In the metric ones, we only use the M in front of it. But what we do use is that you have the diameter. In this case, it was 16. And if it's a fine thread, if it's a coarse thread, you just write M16. Then it's implicit that it's a coarse thread if you don't write anything else. But if it's a fine thread, you will write in, for an example, 1.0, which means that this part here is the distance between threads here. So it's the pitch of it. So for every rotation, the bolt will move 1 millimeter in. So if you rotate it 360 degrees into the threads, it will have moved 1 millimeter inwards. But if it's a coarse one, you just drop this designation, and then it's implicit that it will have. Can't quite remember what M16 is, but I think it's 1.5, which is or it's either 1.5 or 1.25 or something. So it's a bit more. So it will go a bit further when you are rotating it. You can also see here in the example they have put in LH and RH. That is fairly uncommon to put that in. It means that the RH means that it's a right-hand thread, and the LH means that it's a left-hand thread. But if you drop those, you don't write anything there. It will automatically be a right-hand thread. So you only use the LH if you have to specify that it's a left-handed thread. And I'm not sure if you're all aware of this, but usually when you're screwing in a bolt, you would be the idea is to use your right hand, and you will rotate it clockwise. Then you will be tightening the bolt, and then you will be untightening it when you are doing it counterclockwise. So that is a right-hand bolt. But for the left hand, you will do the opposite. So you will be tightening it counterclockwise and loosening it while you're doing it clockwise. The reason that they have these two different directions of doing it is that it was sort of agreed upon long ago that we'll use the right-hand one. We'll go clockwise when we are tightening it. But every now and then you get into a situation where if you use a bolt and you tighten it clockwise, you have something that is rotating, and the rotation of the part will end up unscrewing the bolt. And if you then switch to a left-hand bolt, which you have to rotate the other way in order to tighten it, it will only become more and more fastened with the rotation of the part. So it's a very good example of it is like the Formula 1 cars. For the wheels there, usually for the wheels of a car you have 4 or 5 or 6 bolts on the rim of a car. But the Formula 1s, they only have 1 bolt or 1 nut, basically. That's in the center, which means that on one side of the car, they are going to rotate clockwise, and on the other side of the car, they are going to rotate counterclockwise, which means that if you put right-hand threads on both sides, then on one side it's going to unscrew itself, and you're going to lose both wheels on that side. So then you have to use right-hand threads on one side, and you have to use left-hand threads on the other side in order to avoid serious accidents during the race. So that's a very good example of how you have to use sometimes the left-hand ones. But they are basically the deviation that confirms the rule of using right-hand threads. So you use them when you really have to. So it's always the right-hand threads you choose, so long as you can. There are also other ways of designating it. These are, I think it's pipe threads, this designation is. I'm not quite sure about it. There are hundreds of ways, basically, of designating. There's a lot of types of threads you can have. The metric and unified system are just 2 of them. The thing with the metric and unified system is that so long as you can hit the correct diameter with inches and millimeters, so long as they are the same in the diameter, more or less, they will work, because all of the angles and everything is the same for them. So they will be equal. But when you get to other threads for pipes, outside on pipes and stuff, there's a whole different world. So then you have to really know what kind of pipes, what kind of threads you are designing. But that's a part of the fasteners chapter in the forgot the name of the book now, but the mechanical design book that you have with Torbjørn, the big thick book. So he will take you more through the different kinds of threads when you are looking at it. But we will also be looking a bit at the design, and when we get into Inventor, I will be showing you a bit how it actually works with this spiraling groove and everything. So I think it's a nice complement to what he's doing, because he has to try to do what I'm doing here and just drawing everything on the whiteboard, and it can get really confusing when you start drawing a lot of threads. But if I can, I'm going to get him to tell me when you are doing threads in your lectures, and then I'm going to try to supplement it in the CAD lectures that I'm doing. I'm actually going to show you the 3D models and how it looks. So it's a bit easier to get a feeling of what's actually happening here, because it's a bit difficult to get across on a whiteboard. I know, because I tried to do it with the Norwegian students this spring, so it was really hard to get it across on the whiteboard. In the drawings, we're not only drawing one part on each drawing. When you're creating a production drawing for a specific part, then it's only that part in the drawing, because that's the drawing that they are going to look at when they are going to produce it. But then you also have, once you have created all of the individual parts, you're going to assemble them together. So a mechanic is going to put them together, or a technician or whatever is going to put them together, and what he needs is a sort of guide. So then you create an assembly drawing where you have all of the different parts assembled together, and you show it by doing these item numbers, which is this one. So you create these sort of balloons that will point to each individual part, and the balloon will have a number in it, and the number will correspond to the item number on a parts list, which you will also add into the drawing. Usually it is added on top of the title block. So you have the sheet, and you have the title block down in the corner. So you will add the parts list on top of that. So you will get all your parts close there. So you sort of gather all of your text in one corner. And the parts list usually has the item number, which corresponds to the balloon in the drawing itself. It will also have a quantity, so that it's only necessary to put the balloon on one of the items, unless it's a really cluttered drawing, and it might be necessary to avoid, in order to avoid confusion, that you put balloons to several of them. But it should only be necessary to put one balloon on each item, because you will have a quantity showing how many there are. So, for example, if you have 16 bolts fastening something, then you would have item 1 pointing to one of the bolts, and then you would have quantity 16 of it. And then you would see sort of the pattern of the bolts, so that you would know that, well, you could even count them. Yeah, there are 16 bolts, so all of these 16 are supposed to be that bolt. But the problem is, if you have 16 of one kind of bolt, and 4 of another kind of bolt, and 12 of another kind of bolt, and they're all fairly similar in size, so they will look fairly similar in the drawing, then it might be nice to actually put more balloons on there, just to show that these, either more balloons or one balloon with several arrows just pointing to several of the bolts, just to make it a bit clearer what's going on. It is also very usual to use a part number, and the part number is usually the drawing number that you've done. So when you have created the parts, you would have designated a drawing number in the title field. When we are creating parts here, we don't actually use drawing numbers, because we don't have a system that we're using. But like with Imenco, you had a huge database of drawings. So it was really important to be able to quickly search it and find exactly what you were looking for. So we had everything going on drawing numbers, and they were like there were six numbers in it, and they would be continually, every time someone created a new drawing in Inventor, the database program would automatically assign it the next. So the next one would be, So it would be 27 and 28 and everything. So, and I know that even larger companies, Imenco is a fairly small company, so I know that really large companies, they often have dashes between. So they might have two numbers, a dash, two numbers, a dash, two numbers. Maybe they even have some letters in there. And then they are designation, because this might be, for an example, Statoil. If this was Statoil, 13 might mean that it's on Kårstø and not one of the other processing plants. 45 means that it's a certain area of the processing plant. And then 27 means that it's drawing number 27 in that area. So that you have several ways of doing these part numbers, but it's very common to have it in that parts list. And then usually you also have a description. So it's is it an M16 bolt? Is it a flange? Is it whatever it is? There's a sort of a description, the word or name of the item, which describes it. We talked a bit about tolerances yesterday, so we're going to look a bit more at it now. One way of giving tolerances in a drawing is that you refer to this one, ISO 2768-1 and ISO 2768-2. So you refer to these two somewhere on your drawing, in a text box on your drawing. You refer to them, and then you would say that, for an example, it's a medium tolerance. So a medium tolerance. And that would mean that any dimensions inside the drawing, which are, for an example, 45 millimeters, then we will go over here. 45 is between 30 and 120, so it would have a tolerance of plus minus 0.3. The medium also gives for radii and chamfers, and it also gives for angles, how many degrees. Actually, it gives it in degrees and minutes. And minutes is the sort of decimal point for degrees. I'm not sure how familiar you are with it, but degrees go in the same system as the clock does, in 60, and the count of 60 all the time. That's why you have 360 degrees in a complete circle. So a minute is basically a minute. So if you think 60 degrees would be a complete turnaround, then you would have 1 minute would be the same as a minute on your clock. So basically it gives you 1/60th of the degree as you're going around. So it's a bit difficult to get your head around when you're used to thinking hundreds, tens and hundreds for everything. But once you just sit down and start looking at it, it's usually a bit easier to understand what's going on there. And it is because it's going in a circle all the time. So it's a bit easier to divide it into 60s. So you would have M for medium, referring to the -1 part of the ISO. And you would have, for an example, K, which is the middle tolerance for the -2 part. And the K would give, as we can see, a straightness and flatness, perpendicularity, symmetry, and run. So straightness and flatness is basically how straight and flat should something be. Could there be a slight curve in it? For an example, if you have been grinding something, that's a really rough way of machining it. I think I'll do a better. Let's say you're on an old milling machine, so it's got some give to it. It's not completely reliable when it comes to dimensions yet. So maybe as it was moving across the workpiece, it would have a dip, so that in the middle of the workpiece you would have a slight curve, and then it would go back to the flatness of the original one. So then you can go in here and see for K here, you would have different. You have the dimension range in millimeters, how far is it, and then you can see how much it is allowed to deviate. So the deviation would be, it was supposed to mill it like this, but it ended up milling it like this. The deviation would be the top point, just to see how much is allowed to deviate there. The same with perpendicularity. It's 90 degrees. How perpendicular is this when you are looking at it? Is it within or above the tolerances given? And what you actually do then is that you measure on the shorter angle, on the shorter leg of the angle. So if you have, I have to start removing stuff here. So if I have a part that's, that one wasn't really good. So I've got a long leg of the angle here, and I've got a short leg here. And it's supposed to be 90 degrees in here. So that means that they have to do the tolerance with regards to the length of this short leg. So if the length of this short leg is 200 millimeters, then we would end up in over 100 to 300. So then it will be 0.6 that you are allowed to deviate. That means that you would have the optimum 90 degree angle up here, and you could look at the deviations of, well, actually it's going up here. How many millimeters do we have outside of what and where it's supposed to be up top? It's an easier way of measuring it than actually measuring a 90 degree angle. Because if you're measuring it in how many degrees of an angle you have, it can be quite difficult, especially if you are doing it on small objects. Because the longer legs you have on the angle, the more easy it will be to measure exact degrees on an angle. So as soon as it starts becoming really small, it's easier to actually measure that. Well, you have 250 millimeters here, so you were also, if you continue this line up here, you were supposed to have 250 millimeters there also. So it's actually easier to measure the deviation in millimeters instead. So the clock is 9, so we'll do a break. then we'll continue. So we've been looking at general tolerances that can be given. The thing is, if you refer your drawing to this ISO and you set it, for an example, medium and K, just to give the worker something to look at, then you don't need to put these tolerances. You don't need to put them into the dimensions in the drawing. If it is a 150 millimeter dimension, you don't need to put plus minus 0.5 behind it, because you have already referred to medium in this one. So everything that doesn't have a specific tolerance given will be referred to this one. So whoever is producing it will then look, maybe you have a length of 990 millimeters in your part. You have nothing behind it. So then the guy knows that you have, for example, in a note down here, you have written ISO 2768-1 and medium. So he will know that, well, 990, I have to go in here, I have to see, well, 990 is below 1,000, so it's in here, so that is plus minus 0.8. So then he knows that it is plus minus 0.8 on this one. So you don't actually have to put it in to every, because that's putting in tolerances is a manual operation. After you put the dimension up, then you have to go in and put the tolerance in place. So if you can avoid putting tolerances on most of your dimensions, it is a lot better to just use referrals to a specific standard and a specific tolerance class, because then you don't have to do this on everyone. However, if most of your drawing is supposed to be medium, but this specific dimension, you would want it to be fine instead, then you would have to go in manually, and you would put, let us see, plus minus 0.3. So then you would actually put in plus minus 0.3 in it. Because then you are referring to medium, and medium would be plus minus 0.8. But for this specific dimension, you need something tighter, so you put in 0.3 in it. One other possibility is also that you can use, you can also shift them, so that you can, instead of having a plus minus, so that it is allowed to be 0.3 below and 0.3 above, you can, for an example, shift it to be completely positive also. So even though it's been said here that you want a medium one, the medium one is plus minus 0.8 up here, but you would want it to be on the positive side. So you would set 0 plus 16. So you still have the same range. It's going from minus 8 to plus 8, which is 16, but only now it's going from 0 to 16 instead. So you just shifted it so that it's not allowed to be anything less than 990. So that's another possibility of using them. So using the tolerances is something that comes with experience, really. It's I'll try to incorporate it in the practice test that we're using, and showing how it is possible to use tolerances and stuff. But the real learning that you will do is when you actually start designing stuff on your own and realizing that, I have to do something with the tolerance here to avoid a collision when we are creating it. Yeah. We also have something called ISO fits, and that's more or less the same as these general tolerances, but it is specifically for holes and cylindrical objects that are going into those holes. So basically for shafts and bearings. What they've done here is that they've drawn these lines, 0 lines, as you can see. in every slot here. And their thought is that the zero line that they've drawn, that is the exact dimension. That is, if you hit the diameter exactly, it will be on the zero line. And then they think that, then their thoughts are that the red part, that is the axle, what is going inside, and the blue part is the material around, so it's the hole. And then they put the axle, so the inside will be down here and the outside will be up here. So you have a diameter going up here. Let's say we have a 50 millimeter diameter. So from this line and up to the zero line, there is exactly 50 millimeters. What will happen is, if we use, for an example, let us say the H7 F7 fit, then you have the, see the next one here is, the H7 with a capital H, that is the material itself around the hole. So the capital letter is around the hole, and the small letter is the shaft itself that's going inside. So in this case, you have H7 on the material, and you have F7 on the shaft. And as we can see here, the blue slot for the material is exactly on the zero line, which means that the hole will be, if I do that in blue, the hole will be exactly on the zero line or larger. So it will be a diameter of 50, and let's see if I have it here. That is yeah, we'll do it in a 30 millimeter because I saw the wrong number on my notes there. So you're supposed to have a 30 millimeter hole. What the hole will be from 30, and it will go from 0 to 0.25. 0.025. So that will be the dimension of your hole. Now for the shaft, let's see if I have a better red one here. The shaft is supposed to be inside here. And you can clearly see from the figure here that it's far below the inside. So it's been shifted quite a bit down. So it has and it is minus 0.025 to minus 0.050. So it can be quite a bit smaller than the hole in this case. And the thing is, instead of having to do all of these dimensions and stuff, all of these tolerances, going into the tables, trying to figure out exactly what it is, writing in all of these numbers, instead we can just do the and we do the F7 on it. So we put in the nominal dimension that we're supposed to have, 30 millimeters in diameter, and then we just designate F7 on it. And that will automatically give it this tolerance. And the same with the hole. 30 millimeters, and we designated, was it H? H7 there. Just write in H7, and then we get the correct one. Whoever is manufacturing it will have these tables with the corresponding tolerances for F7 and H7 and everything. They will have that with them in the workshop. So it's completely fair to just write 30 F7 on it. That's not a problem at all. What you can do is, I'll show you later on in Inventor, is that you can designate F7 as the tolerance in Inventor, but you can also click the option that it's actually going to show the tolerance. So that you don't have to actually figure out the tolerance yourself. You just put in the F7, and then Inventor will add what the exact tolerance will be. So it will just put it in for you in the drawing. So that's one of the nice automation parts that are in Inventor. The isofits are used because this first part, which was up here, is, as it says up here, clearance fits. Like this one, you are going to have air between the shaft and the wall of the hole, so that it's going to slide very easily inside there. There's not going to be any problems getting the shaft inside. When the tolerances here are fairly tight, so if you have the minimal clearance fit in it, they can actually be touching on both sides. But you will still be able to slide it in if it's been manufactured correctly. And then you have these transition fits. So the clearance fits are mainly used if you have a movable part. If this shaft is going to rotate, then you usually use a clearance fit in some way. And then you also have the transition fits, which is sort of a cross. It is starting to be a collision between them, so they're starting to have a bit of trouble. Maybe you will have to use a hydraulic press to actually push the shaft into the hole. Or maybe you will use the old-fashioned way with a sledgehammer or something, and you will just tap it in until you get it inside. And then you have the interference fits, which are these. Those are even worse to get in. So for the extreme ones, then you have to be shrinking them as it's called. So you will be heat treating them with cold. You will be cooling them down until they reach a temperature where you have actually shrunk it enough to make it fit in. So because as you reduce the temperature on metal, you have this thermal coefficient. I think you did a lot of it in your statics course. You calculated some of it with the thermal coefficient. So if it gets hot, it expands, and if it gets cold, it contracts. So actually what you do is you cool it down enough. And in the car industry, what we usually did was that we had a CO2 tank. So we had CO2 under pressure. And when you release that, it gets really cold. So then we just sprayed it with CO2 until it got cold enough. So there was a lot of frost forming on the shaft and everything, and you had to have gloves to touch it, or else your skin would stick to the metal. So when you get that cold, about minus 30, minus 40 degrees Celsius, then you had actually shrunk it enough that you could fit it inside the hole. And then when it returned to room temperature, it would expand, and then it would be completely stuck inside the hole. You couldn't budge it at all. You would have to cool it down again if you were going to get it out. So that's a good way of getting them stuck without using welding or anything like that. So it's something that's it's fairly much in use in the car industry. I haven't seen it much used in the subsea industry, but I haven't seen all of the subsea industry by far, so it might very well be areas where they use it. There are also geometric tolerances that can be set. What you do then is that you give a datum, it's called. So you specify a datum area. So you give it, like in this case, they have used several datums, so they have A, B, C, and D. And this pertains to an axis or a surface or an edge or anything. And it means that any tolerances that you give with that datum letter on them will be with regards to that. So, like for the A here, which is the axis. So when you're giving this tolerance, then it's referring to this axis. So the tolerance is with regards to the axis of the shaft. And what you use the geometrical ones for is basically making stuff stay in place, not just by saying that it's going to be placed exactly here by giving a dimension, but also by telling it to be, for an example, concentric. If you have a hole, if you have a shaft that you're supposed to have a hole in the end, it's supposed to be exactly in center here, and it's going fairly deep in, so maybe it's going this far in or something, and it's going to be along the axis of the cylinder. Then you can, and it's very important that it's exactly on there. You can use tolerances, geometrical tolerances, to state the importance of this. Because if you don't use a specific geometrical tolerance, it will be as exact as the machine can get it with the settings that they use to achieve all of the other tolerances. So then you are sort of at the mercy of the machine and the operator of the machine. But if you specify it, then they also have to put the variable into their account that, well, we have to follow the center line of this cylinder when we're doing it. So we have to be extra sure that we get it in the exact position. Here are just some short examples for it. Like if you want them to be parallel, two surfaces to be parallel. Perpendicularity, that they are going to be exactly 90 degrees, or as exact as you can get it. Cylindricity you can show. Concentricity, that they are have the same center line. Cylindricity, that it is actually a cylinder all the way through, that it hasn't been twisted or anything along the way. Symmetry, that you have the perfect symmetry around it, more than just using a symmetry line, as we looked at yesterday. Then you would actually specify that this has to be really perfect symmetry, or as perfect as you can get it, basically. Yeah, those are just a few quick examples. There are many of these tolerances that can be set. And to my experience, most engineers that use them in their drawings manage to use them incorrectly. So, so they haven't really done their homework. They haven't read how they are supposed to use these symbols in the correct way, so that when they put them on the drawing, they are putting them as they think they are supposed to be. But they haven't really confirmed it by reading the theory on how it's supposed to be used. So if you end up in a situation where you think that you are in need of using a geometrical tolerance, I would highly recommend that you sit down, you take a half an hour or something, and you just read yourself up on this and get sort of refresh your memory on how does a geometrical tolerance work, exactly how am I supposed to put it into my drawing, the symbols and everything, where they're supposed to be placed, in order to get it correctly. Because this is something that you fairly seldom use, so that every time you use it, it is useful to refresh your memory when you're going to use it. Surface finish. When you're machining materials, you won't get a completely flat surface. If you go down to the microscopic level, it will look more or less like this one. So you will have valleys and peaks and everything. If you do a cut through it and then you put the microscope to the edge of it. And this is because, like, if you are in a lathe and you're turning a cylinder, so you have the material is turning around like this, and you have a cutting tool, and it is moving along it. So it will cut a spiral groove all the way. But the blade isn't completely... if you look at the blade from the top, the blade looks more or less like this. So it's got a rounded tip. So it will create spiral grooves that looks almost like that along the entire length of the tool. If you decrease the speed at which the tool is moving, then you will of course create smaller and smaller parts. So if you specify a very fine finish on your material, it means that all of the tools that they are using to create it have to move very slowly. So it will take a lot of time to achieve the surface that you have specified. So this is something that is very important to keep in mind when you're designing stuff, because if you specify too fine of a surface where it's not needed, then you're going to pay a lot of money for the machinists and the operators and everything to actually create this surface when it wasn't necessary, when they could have maybe had twice the speed on their machinery and ended up with doing it for half the cost, basically. So it's something we need to take into account. One of the ways of specifying it on the drawing is to use the highest peak of the profile, or the arithmetic mean of the profile. So RZ or RA. So the RZ, which is the highest peak, it simply designates what is the maximum height that is allowed in these mountain tops and valleys that you have. What is the maximum difference in height that you can have on them? And the arithmetic mean is basically just the mean value of the height of all of the tops. Some people prefer to using the RZ, some prefer using the RA. It's not a huge problem, really, because you will be giving different numbers for them. It is a problem if you start to confuse. You give the numbers for RA, but you have written RZ in front of it, because then you will have something completely different from what you intended. So long as you are consistent in what you're using, that's the best way of doing it. The way we show surface finish is that we draw these symbols, which we have up here. There are 4 basic kinds of surface finish symbols, and the very basic one is this. So this tip here is supposed to be in contact with the surface that you're specifying, but sometimes that's not quite possible, so you can also use an arrow to specify it. The first one, which is completely open, means that all manufacturing processes are allowed. So it means that you don't really care how they achieve the surface finish, so long as they deliver the correct surface finish. It's not your problem how they do it. Sometimes you need them to remove materials, so that even though the material is within the correct tolerance, they still have to remove a thin layer of material from it. So then you are telling them that you have to remove some of the material. So this is often used if you are, for example, using a steel plate, huge steel plate, and you have bought it to have a thickness of 5 millimeters, and you have also designated on the drawing that it's supposed to have 5 millimeters, but then you will have the surface finish that's coming directly from the mill, where they have treated it and everything and created it. So you won't have a machine surface finish on it. So then you can designate that they are going to remove material and have a specific surface finish on it, because then you will get a nicer surface on it. So even though the dimension is correct, they still have to run their milling machine across it. And then you also have material removal not allowed. And that is often used if, like in the subsea industry, you are designing something using existing pipes. So if you have a length of pipe that you're going to use to create a product, and it's not necessary for them to turn it or anything, do anything to the surface of it. Maybe they're going to do something in each end because you're going to weld something to it or whatever, but they don't really need to do anything with the entire length of the pipe. Then you can put this one up, because what often happens with pipes is that they have tolerances for their production. When they're producing piping, they don't have plus minus a certain amount of micrometers. They might have plus minus 5%. And if you have a 12-inch pipe, so you're in this size, then plus minus 5% starts to become quite a lot. But it might not be necessary to actually remove material in order to get it into the designated. It's not a problem that it's larger than it's supposed to be, basically. And then you have one addition that you can do. You can do this sort of circle on the top there, and that means that all of the surfaces around it are supposed to be this surface finish that you have designated here will count for everything, all of the surfaces around the entire part. So on the entire contour of it. So here you can see it can be as easy as doing one of these two. You just put in RZ and the value behind, or RA and the value behind. It can be that easy to designate it, and that's what's mostly being done. Or if you're doing something really, really, really special, you can start adding a whole load of information onto this symbol. But usually that is something that is, when it's starting to get that particular, it will be nice to have a dialogue with whoever is going to machine it, so that you know how do they operate, how do they interpret this when you're putting it in. Because that is one of the best tips I can give you, that that actually have taught me a lot, is to just keep an open dialogue with whoever is producing the stuff that you're designing. Because they will come back to you and might tell you that, well, this tolerance fit that you put in this one, it's going to become a bit loose. So I would maybe tighten it up a bit, because I see what you're intending here. And then I just revise my drawings and tighten up the ISO fit on it, and then they go ahead and create it. It's a very, very useful synergy to have, to actually talk to the people that are producing stuff. Welding specifications also have their own symbols. I think I missed one after surface finish there, but you can see on the other page of next page after surface finish, before welding specification, you see a table which shows the approximate surface finish you get from different kinds of operations that you can do. So you have on the lower part of the table, you have machining operations, and you have drilling, turning, milling, honing, and just showing you the different values that you would have generally if you're choosing that way of machining them. So the welding symbol is fairly similar to the surface finish symbol. As you can see, you have the arrow going up here, and then you have some more information that you can add on top. You have the same stuff with the weld, that you can put a little circle on it to show that you're going to weld all the way around something, instead of sort of putting several welding symbols on to show that this goes all the way around. You can put that circle on. You use the at least here in Norway, I think most of the world use it, but we use the A measurement when we are specifying the thickness of a weld. Torbjørn will take you into the specifics on how this works. I would digress completely if I start talking about that. In this case, we have fillet welds, which are the blackened parts of this drawing. So here they are shown by symbols. So what they've done here is that this symbol up top, they have used A4 up top and A4 below the line, and also a triangle on both sides, which means that it's on both sides of the plate. So you're supposed to do it on both sides there. While the other one, it has nothing on top of the line, but it has a dashed line below with A3, and that is this one. So it shows that it's pointing to this corner, but it is actually the other side of the plate that's going to be welded. So it's a bit of you can easily confuse people with welding symbols if you're not careful. You can also add some extra information on top of these triangles. You can add an arc showing if it's to be a concave surface, so that if they are going to weld it, are they going to weld it so that it is sort of you have the two plates, and when they are welding it, it will often look like this afterwards. So it will be a bulge if you cut it. But then they can go over it with a grinder and they can sort of grind it down to become more like that. So that is one way of showing it. You can also put a flat line on top, and that means that they will grind it, but they will only grind it until it is more or less a flat surface. And then you can just allow it to be this bulge that it was from the start. And then you have the other one here, which means that the weld surface is notch-free, which means that they have to pay particular attention that they get a very good weld all the way. So they can't have sort of small bubbles where they have where it hasn't been welded properly. Because those small areas where there isn't any weld materials, those will actually be the weakest parts of the weld. So you can actually end up with the weld not being as strong as you have specified if you have notches in it. But that's a bit up to you when you're doing your design calculations. Are you using a very large safety factor? Then it doesn't really matter how the weld looks like as long as it has the correct thickness. So considerations. We need to consider the function of the parts that we are creating. We need to consider how it's supposed to be fabricated or produced in the workshop. We need to consider quality control. Is it going to be easy to quality control the dimensions on this particular item, or should we maybe try to redesign it a bit to make it easier to ensure that the quality is being upheld? Is it easy to interpret the drawing? That's something that we really need to think about when we are creating drawings. And for the main view of the drawing, it is supposed to show the most information. It's supposed to be coincident with the function of the item, so that the main view, which is the first one you choose on your drawing, it is supposed to show what you would consider the front of the part, so that where you would look at it when you are using it, so that it shows how it functions. We should try to place it naturally on the sheet so that the projected views get the correct locations and everything. Other views that we use, like sections and detailed views and stuff, they also need to be easy to interpret the necessary information that you put into them. And there should be a uniform distance between all of the views so that you don't have a couple of views that are really bunched up in a corner and then you have a huge open space to the next view. That looks pretty messy. Here is the drawing checklist that's on Fronto. And I'm just going to go through an example drawing now where we can look a bit at everything. So here's a drawing. It's a bit shame that we can't see everything up here, but so we start off with geometry. I see that probably some of the other points are going to be lost up there as we go along, but we'll see. Is the part shown in its operating position in this case? So the main view on this one is this view over here, and I would call that the operating position because usually when you look at a valve you will look at it from the side and you will have the handle on top to do it. So that is a very nice view for it. Are all necessary views and sections in place? Well, we have the front view there. We have projected it over to this side so that we can see the side and the flange there. We have projected it downwards so that we can see the top. We've also created a section B through here, just to show that it might be a bit difficult to see up here, but it is actually the wall thickness here is thinner on the sides than on the tops, just to show that it's not completely cylindrical. It's more elliptical. And we have a section going through here just to show the entire inner cavities of it. And down here there's a lot of details going on, so there's been put a detail view in just to get all of the dimensions in place. Are projected views placed correctly? Yes, we have. Here we have the front view, and it's been tilted over to this side, so we are looking at it from that side there. And it's been tilted down here, so we're looking at it from the top. So those projected views are placed correctly. Are sections marked consistently? Sometimes, especially in Inventor, it will put these letters on automatically. But that means that if you put in a section here, that is your A section, and you put up a section here, your B section, but then you figure out, I wasn't quite happy with the placement of that section, so I'm going to delete it, and I'm going to put up a new one here. Then that one will suddenly be C instead of B. And then the detail view will become D when you put that one in. So it's just nice to check that you don't have any letters missing there, that you actually have A, B, C. Because if you suddenly go from A, C, D instead, then whoever is reading the drawing will start looking, well, where is B? I've missed B, where is it? And then they might start wondering, is there a second sheet that I have to look at? Is B on the second sheet instead? So it's nice to just keep it in alphabetical order. Are section lines straight with 90-degree angles? Well, in this case, we only have straight section lines. We don't have any 90-degree angles, so that's okay. Are the section arrows pointing to the correct side of the section line? Well, we have a section line for A here, and we are showing it on this side, and we have the arrow pointing to that side, so that's correct. We have the section line for section B with the arrows pointing this way, and it is shown on that side of the section line, so that is also correct. Although it had to be moved down here because there was simply no room up here. And we are not supposed to section teeth, wedges, etc. if they are in the plane of the section view. That's not a problem here because we have a single part. we don't have an assembly, so we don't have any well, teeth of wedges we could have had if we had been drawing a gear, a cogwheel. Then we would have teeth on the cogwheel, so then we would have had to not section those. Do not section shafts, bolts, washer, nuts, fasteners, etc. And as I said earlier, we don't have an assembly, so that's not a problem. We don't have any bolts or shafts or anything in this drawing. Are all center lines, center marks, and symmetry lines in place? So then we have to look. We have the inner hole going through here is circular, while the outer part is elliptical. So there should be a center line going through the hole. That is correct. There's also a center line going from top to bottom. There's center lines through these holes. We also have center marks on the holes there. We have a pitch circle diameter all the way around, a center mark on that cylindrical part. We even have the center lines here. And here we seem to have everything. And also here. So that looks good. We seem to have everything in place. That is actually one of the most common mistakes in technical drawings, is to forget to place some of the center lines and center marks in there. Have the general geometrical tolerances of the drawing been defined? So here we have general tolerances and surface finish. The ISOs have been defined there. So that is correct. Have specific geometrical tolerances been set correctly in the drawing? Let's see, we don't have any tolerances on any of the dimensions, so that wasn't a problem. We are only using the general ones. We are not using specific tolerances. So now we are in a bit of problem here. We can't see the top one. Let's see, place dimensions from a defined machined edge. So that is more for like the length dimensions here. So we have used this one as this side as the base point, moving over to 19. We have the 200 for the entire length, and then we have the base point here. These are symmetrical across the center. So mostly it has been done here. Due to the shape of the part, it's not always possible to actually do that. Sometimes you have to choose other edges to start your dimensions from, but it has been done as far as it can be done here. Avoid dimensions on hidden lines if possible. Well, we are not showing hidden lines on these three views, so that's not a problem. Are all unnecessary dimensions removed or made into reference dimensions? And we don't have any of those, I think. Nope. No reference dimensions. Are diametrical and radial dimensions placed correctly? So we have the dimensions. They have been pulled out of the drawings. We have the radii. They have been put in here. Looks pretty well. As you can see here, we have the holes in the top. They have just been pointed to with a diameter. And that is also a function you can use in Inventor. If you've created holes with the hole function in the 3D part, you can use a specific dimensioning function for holes in here. So then it will do all of the information that you have put into creation of the hole in the 3D part will be transferred to the 2D drawing. So let's see, is the drawing in a standardized scale? In this case, we don't have any scale shown. We only have scales shown on the sections, and those are standardized, so that's okay. Are all the main dimensions and the dimensions outlining interface towards adjacent parts present? This basically means main dimensions is, of course, for production of the part. But dimensions outlining interface towards adjacent parts, that is, as in this case, we have 3 flanges, one on each side and one on the top. So are the dimensions present for knowing that this is going to fit to the next part that's coming here? And we have that because we have the pitch circle diameters giving us the placement of the holes and everything. Are all the dimensions that define the function of the part present? They should be here. We can, if you want to, you can try to figure out if there are any dimensions missing, but I think we are closing in on break here. So this is the last thing we have for today, so I thought we'd just do it, finish it, and then you can relax until hydraulics. All the dimensions that are necessary to produce the part grouped in relevant locations. The reason for this one is that for complicated drawings, it is often nice to try to group dimensions. Like here, these have been grouped. Those are for the bottom there. When you come up here, you see that all of these, the rest of the dimensions that give this vertical part of the hole, are also given there. So they have been grouped in the more or less same place, as much as they can at least. That is often just to make it, to ensure that you don't have to sort of switch between a lot of views in order to create a specific part of it. Have the general tolerances of the drawing been defined? Yeah, we had those there. Have specific tolerances been set correctly? You know, we have already been through that. Have isofits been set? We don't have any shafts and holes. Avoid having more than one set of tolerances, isofits, on one function. That is just a sort of reminder that make sure that you haven't put double tolerances on something. So it's just it's something that can happen if you're in a hurry when you're creating something. So when you then go through your checklist, you get a sort of a reminder to just remove one of the tolerances if you've put a double one in there. So for production, has the material of the part been defined? Yes, we have the material down in the corner. Has the general surface finish been defined? We have the general surface finish there. And we have no other surface finish symbols, which means that everything is supposed to have that surface finish on this one. Have specific surface finishes been set correctly in the drawing? Yeah, we don't have any of those, as I just said. Is there information about the desired production method, production sequence, if applicable? The production sequence and method, that is more if you you need them to machine this part, then weld something onto it, and then machine some more. So that would be an example of how you're supposed to put these up. In this case, this is just one part, so there's not anything to add there. Have relevant notes been given, such as break sharp edges? That has been given as a note down here. Break the sharp edges to 0.2 times 45 degrees angle. Are all the parts documented in the parts list? Well, this is a single part, so we don't have a parts list for it. If it had been an assembly, we would have needed to have all the parts in there. Have balloons been placed to reference the illustration of each part to the item number in the parts list? Well, again, it's not an assembly, so we don't have that. Has the title box been filled in? Yes, we have me as the designer, Torbjörn as the checker, and Einar as the approver. It's been done here at the school. It's a valve house. I haven't given it any drawing names because we don't have any system for drawing names. It's the first edition, revision A, and we have 1 of 1 sheets. The 1 of 1 sheets, that's an automated part in